Hello everyone, it's my honor to be invited to speak here. I'm Hongqiang, a master from Hebei University of Technology, and my topic today is Dependency-Aware task offloading and scheduling in multi-server and multi-application in vehicular edge computing. I will introduce my paper in the following 5 aspects. First is introduction. The growing developments in vehicular networks and vehicular internet services have yielded a variety of computation-intensive applications, resulting in great pressure on vehicles equipped with limited computation resource. In vehicular edge computing scenario, vehicle can offload computation-intensive applications to mobile edge computing server for execution to reduce time. However, there are some challenges. Vehicles with high mobility and multiple tasks with dependencies. Traditional offloading algorithms are not suitable for the requirements of the computation-intensive applications in vehicular edge computing scenario. Current solutions can be divided into 2 types: offloading applications to cloud server, offloading applications to other MAC server. But there are the following problems. Offloading applications to cloud server will bring extra transmission delay. All tasks in same MAC server and the local computing resources and the collaboration between MAC servers are not considered. Most of them did not consider the dependencies between tasks. Above all, we proposed our scheme. Next is the system model. First is our network model. As shown in the figure, there are N vehicles and M ICUs in the network, all covered by base station. Each ICU equipped with a MAC server. Each vehicle have one application with multiple dependent tasks. Every MAC server and vehicle have limited computing resource. ICUs and base station communicate through wired connections. Base station have the global information. Within the wireless coverage of the ICU, vehicle can offload task to MAC server. Specific definition can be seen in the left. This is our task model. The relevant attribute information of the application is described by a tuple denoted as AN. Each application have KN dependent tasks, so they can model as a DAG task graph in the right figure. Entry task is D11, exit task is D110. Each task have a corresponding attribute information. We use a for tuple to describe attribute information of the task. DNK, ONK, CNK, and TNK. There are 2 binary variables, dependency variable and decision variable. Tasks can be offloaded to MAC server or executed in vehicle. This is our computation model. Sometime variables, movement time, residence time, transmission time, ready time, earliest start time, execution time, earliest finish time, and application finish time. For movement time, residence time, and transmission time, there are 2 cases. Predecessor task executed in vehicle. Successor task offloaded to MAC server. In this case, vehicle transmitted data to MAC server. And in second case, predecessor task offloaded to MAC server. Successor task executed in vehicle. In this case, MAC server transmitted data to vehicle. Binary variable XNKM as a scheduling result of tasks on server SM. In order to ensure the completion of the task, we make a constraint that the sum of transmission time and execution time not exceed the residence time in server M. When we got earliest start time and execution time, we can get earliest finish time. When task is scheduled, the earliest finish time is actual task finish time. When the exit task is finished, the application is also finished. So the finish time of exit task is the application finish time. After many variables, we got an optimization model with some constraints. Constraint C1 indicates that if the task is offloaded, it can only be offloaded to one MEC server. C2 indicates that the task completion time is less than the task deadline. The purpose of the model is to minimize the average completion time of all applications. Those two binary variables make this optimization problem is hard to solve. It's NP hard problem, so we proposed a heuristic optimization algorithm to solve this problem. Then I will introduce our algorithm. Our algorithm is dependency-aware task offloading and scheduling multi-server and multi-application, DSMM. It can be divided into two parts. First part is the task prioritization. Ideas come from the latest article. We define three variables: latest finish time, select latest finish time, and the latest start time. And we use latest start time as the priority indicator of the task. As this is a normal case in offloading scenario, upload, execution, and download process all within the readiness time. Besides, there are two cases of transmission interruption due to the high mobility of the vehicle. First is upload interruption case. In the left, the task input data upload process span to MEC server. The current MEC server can be selected, and the next MEC server will be selected. Similarly, if the execution of the task cannot be finished within the readiness time in the MEC server, the next server will be selected to decide whether to offload. Second case is return interruption in the right picture. When task result is returned and interrupted, MEC server cooperative transmission strategy is used. Current MEC server transmits this task result to the next server, and the next server transmits this result to vehicle. Then, the second part of our algorithm is task scheduling. There are 7 steps. First, construct a priority queue according to the latest start time. Select the highest priority task and calculate the ready time. Select the MEC server from the starting position of the vehicle along the direction of the vehicle. Calculate the EFT, earliest finish time, according to the formula. And consider whether an interruption occurs during this process. Then calculate the EFT for local execution. Compare the two variables. Select the smallest EFT and decide the offload strategy. This loop until the priority queue is empty. In this algorithm, factors such as task dependency, server collaboration, and vehicle mobility are considered. Similarly, due to the nature of task dependency, there are gaps in the scheduling sequence on the MEC server, and the insert-based strategy is used in the scheduling process to improve resource utilization. Based on our mathematical model and our algorithm, let me introduce our simulation. The first is experimental parameter setting, as shown in the table. M is the number of MEC server, N is the number of vehicle and the application. 2FM are the computation resource of MEC server and the vehicle respectively. Vn is the vehicle speed, B is the bandwidth, P is the transmission power of the vehicle, Gm is the channel gain between the vehicle and the RSU, and 0 is the background noise. 10 is the deadline of application. D is the input data size of application. DNK and ONK is the input and output data size of task. CNK is the requirement computation resource of task. Our algorithm is called DOSMM scheme. There are two schemes for comparison with two metrics, average completion time and completion rate. First, we can see the DOSMM scheme is more better, has the lowest average completion time than other schemes. The blue line is DOSMM. Second, DOSMM scheme will keep highest completion rate with the increase in the number of applications. Third, the studies in different number of applications and different coverage of the MAC server. As the coverage of the MAC server increases, or the number of applications increases, the application average completion time is increasing too. The last is the conclusion. In this paper, we studied the problem of offloading multiple tasks with dependencies in multiple applications among multiple MAC servers in vehicular edge computing, and constructed this problem as an optimization problem. In order to solve this problem, we designed a heuristic algorithm. In this algorithm, factors such as task dependency, server collaboration, and vehicle mobility are considered. By comparing with other schemes, we proved the high performance of our algorithm through simulation experiments. Thanks for listening.